sign depends on the charge of the diffusing ion. Only a small number of ions need to move to create this potential, so bulk ion concentrations don't change. Equilibrium potential is the membrane potential at which the electrical force on an ion exactly balances its chemical gradient, resulting in no net movement of the ion across the membrane. This potential is calculated using the nearest equation, which determines the voltage required to bring an ion to electrochemical equilibrium. Examples with sodium: if a membrane is permeable only to sodium and its concentration is higher on one side, sodium will diffuse to the other side. This creates a diffusion potential, with the original side becoming negative. This negative potential eventually becomes strong enough to pull sodium back, balancing the concentration gradient. This is the sodium equilibrium potential. Example with colloid: if a membrane is permeable only to colloid, its diffusion down a concentration gradient would make the original side positive. This positive potential will eventually balance the colloid movement. This is the colloid equilibrium potential. Driving force and current flow: the driving force on an ion is the difference between the actual membrane potential and the ion's equilibrium potential. Represents the net electrical and chemical force acting on the ion. Current will flow if there is a driving force on the ion and the membrane is permeable to it. The magnitude of the current is proportional to both the driving force and the membrane's permeability to the ion. Listing membrane potential: the steady state potential difference across the cell membrane around -70 MV for a nerve cell, primarily determined by the diffusion potentials of permeable ions, with the most permeable ions having the greatest influence. Dominance of potassium: the resting potential of -70 MV is very close to the equilibrium potential of potassium and far from the equilibrium potential of sodium. This indicates that at least the nerve membrane is more permeable to potassium than to sodium. Indirect role of the sodium-potassium pump contributes to the resting potential by maintaining the crucial concentration gradients for sodium and potassium while it's electrogenic. This direct contribution to the membrane potential is minimal. Action potentials: rapid, all or none change in membrane potential that